We're going to continue our discussion about MOSFET amplifiers. We already discussed last lecture about common source amplifiers, in which you have the input is at the gate and the output is at the drain, and the source is just common between them. And here is the equivalent circuit for it. After our analysis, we found that EV is equal to minus GMRD. So we can control this EV to make it with high value if we control RD and also the biasing, which will determine GM. Our input is infinite, which is very good. And RO is equal to RD, which is from moderate to high values. And one note here is that you can say, okay, I will increase RD to increase EV. But then you should remember that if you increase RD, yes, EV will increase, but RO will increase as well. So it's a trade-off here, okay? You can't just go with any value for RD. Okay, so let's now continue the discussion with another two configurations, which are the common gate and the common drain amplifiers. So let's start by common gate amplifier, in which the input is at the source and the output is at the drain here, and the gate is just common between them. Okay, so let's draw the equivalent circuit for it. You know, guys, we take two equivalent circuits and we say that both are equivalent, just like BGT, and you can use any of them. It's usually better here to use a second version in which the gate is at the bottom and you have the source on the left and the drain on the right. So here is the equivalent circuit. Here you have the gate, and remember that the gate has all the time a gate current equal to 0. Okay, so whenever it's connected here, the current into the gate is 0. And you have here GM VGS, and here is the drain, and here is the source, and this is 1 over GM. Okay. And remember, the polarity of VGS is in that way. The positive is always near the gate, and the negative is also. So because it's called VGS, the voltage of the gate with reference to the source. The source is negative. Okay, good. So let's continue the rest of the circuit. Between the source and the ground, there is our signal and V signal. And remember, the input is just at the terminals of the signal, and here is also our input from that location. And the gate is connected to ground, and the drain is connected to the ground through RD. And that's it. And here is VO. Okay, let's determine EV first. So EV is equal to VO over V input. VO is the current through RD, which is GM VGS. And remember, this current is flowing from bottom to up, so it's an opposite polarity with VO. So it's minus GM VGS RD over V input. And V input is just equal to the gate source voltage, or the source gate voltage in that case. So it's minus VGS. Remember, VGS is positive negative, but V input is positive, positive negative, and V input is positive negative. So it's opposite. So minus will go with the minus, VGS will go with VGS. So it's GM RD. So first observation here is so number one, same as common source amplifier gain in amplitude, but it's non-inverting, which is good, non-inverting. Also, most of the cases, we don't care about the inversion of the output signal. And non-inverting means there is no phase shift. Remember, with common source, the AV was minus GM RD. So the output is out of phase with the input. Good. And this is also good, good amplification. Just like common source. So let's determine our input now. Number 2, our input. Our input is just, V input over I input. And I just assume this is I input here. So it's basically 1 over GM. So the resistance between the source and the ground is just 1 over GM. And this is usually, here is the observation, low input resistance. So it's not, till this moment, not inverting, which is good, good gain, okay, but it has low input resistance, different from the common gate amplifier, common source amplifier, I'm sorry. Okay, number 3, RO. So for RO, we remove the load. Basically, we don't have a load here. I mean, separate load. Okay. So if we draw the circuit after putting, Vx and Ix as usual, we have RD. Then we have our GM-VGS. And we have here 1 over GM. And we have our signal, and we're gonna cancel the source, the independent source. So ROA is equal to Vx over Ix. Okay. When you cancel the source here, which is V signal, basically VGS will be equal to 0. Okay. Because the current here is equal to, since there is no source, the source is 0 now. So 0 over the resistances, which is R signal plus I1 over GM, is equal to 0. So V signal is equal to 0. So GM, VGS is equal to 0, or open circuit. So Vx over Ix is just equal to RD. And here is the observation now. This is moderate to high resistance. So that till this moment, we didn't gain anything useful, okay? Because basically this is has lower input resistance than a common source amplifier, okay? Same output resistance, same amplification. Yes, it's not inverting, but most of the time the inversion, doesn't affect us so much, and we can just ignore it for most of the applications. But we lose something, we lose our input. But turns out that there is some applications, like the example we're going to see today, in which you need input resistance. Okay. For example, when you interface with a coaxial cable, if you guys study this in field theory, when you have a coaxial cable, you need a proper termination for it. So you need a load resistance, which has resistance equal to the equivalent resistance of the coaxial cable, so that there will be no reflections. Okay, so for such applications, we will need common gate amplifiers or common base, which is the corresponding one in BJT transistors. Both have very low input resistance, but it's beneficial for such applications. Okay, let's now go to the common drain amplifiers. So this is the last, last configuration we have. So with common drain amplifiers, we have the input is at the gate, as we see here. The output is at the source, and the drain is just common between them. Okay, so let's draw the equivalent circuit and see. So I'm gonna solve this particular example using 2 solutions, and basically they will merge to the same stuff, because basically it's the same circuit. Okay, so I will gonna solve it first using the first equivalent circuit that we used to do, then the other version of the equivalence, just to show you that if you use both, okay, the problem may get harder or easier, but you should get to the same conclusions or the same numbers. So let's do it first with the first equivalent circuit, the one we just used to do. Okay, so let's do it first using So solution 1. So this is here is the source, here is the gate, here is the drain, GM VGS, and here is VGS, and it's open circuit between the gate and the source. So the source is connected to RL like this, and here is VO. The drain is connected to ground, and the gate is connected to our signal V signal. And where is the input? The input is in the terminals of the signal, so between the gate and the ground. So this is the input. Okay, and of course these are the two terminals from which we get our input, and here is our output between this terminal and this terminal. Good. So let's do our analysis now. So AV number 1, AV, VO over V input. Okay, VO is equal to the current here multiplied by the resistance RL. The current is GM VG because this current just it's open circuit here, so all of it will go to the RL. So here is GM VGS RL over V input. V input is from that loop. It's equal to V output plus VGS. So it's equal to VGS plus V output, and V output is GM VGS RL. So VGS with VGS with VGS will go away. So AV is equal to RL over RL plus 1 over GM. Usually, let's write it, usually RL is much greater than 1 over GM. And remember, 1 over GM is the input resistance of common gate amplifier, and we say that it's low. Okay, it's usually very low. So RL usually much larger than 1 over GM, and in that case, RL plus 1 over GM approximately equal to RL, and in that case, EV will approximately equal to 1. And here is some observations on that. So basically, no amplification. Although it's called amplifier, but there is no amplification. Actually, it's attenuation. It's a slight attenuation at the output, because this is basically less than 1. But since 1 over GM is much less than RL in most of the cases, so it's approximately 1. Okay, it's non-inverting, which is good because it's a positive. So the output has the same phase shift as the input. And since it's 1, since VO is at the source and V input is at the gate, we call it source follower. Just like common collector amplifier, we call it emitter follower. Okay, because the voltage output is at the emitter and approximately equal to the voltage input at the base, so we call it emitter follower. Okay, here is exactly the same. And we will see in a moment it's the same characteristics as well. Okay, so tells it, and by the way, EV now is approximately 1, and also common collector has approximately 1 for EV. So let's go to the R input now. Number 2. our input. So our input basically is V input over I input. It's equal to infinity because I input is 0. It's open circuit here. Open circuit, which is very good. And remember also common collector amplifier or the emitter follower has also very high input resistance. Okay, so far so good. Let's now see RO. So we're gonna remove RL and put Vx and Ix and see, and of course cancel the source. So we have here ground, then GM VGS, and here is Vx, and here is Ix. Oh, sorry, Ix, and I'm gonna cancel the source. So we have something like this. This is our signal, and here is VGS. Okay. So RO is equal to Vx over Ix. Okay, what is VO? So what is Vx? From that loop here, Vx is in that way, VGS is in that way, and let's assume there is a current in our signal in that way as well. So we have Vx plus VGS from that loop plus I, let's call it I, multiplied by our signal equal to 0. I is 0. So this term is 0. So basically Vx is minus VGS. How about Ix? So Ix at that node here, the current input is Ix. Also GM VGS is also input, so it's also positive, equal to 0. There is no other currents. So from that Ix is equal to minus GM VGS. So let's now compensate in RO. So RO is equal to Vx, which is minus VGS, Ix, which is minus GM VGS. So minus will go with minus, VGS will go with VGS. So this is 1 over GM. 1 over GM. This is usually very low. Remember, this was the input resistance of common gate. So this is very low input resistance, which is very good. And remember, also common collector amplifier or the emitter follower also has a very low output resistance. So till this moment, we are, have an equivalent version of the emitter follower here, but it's called the now source follower with exactly the same characteristics: high input resistance, low output resistance, and EV approximately 1. Okay, and the same applications as well. This will be used again as a buffer, we can say, between very small loads and very and voltage sources with very high internal resistances. Okay, if you remember, guys, this was the application for common collector amplifiers. So let's now solve the same common drain amplifier using the second version of the equivalent circuit of the transistor, and we'll see that they are both equivalent. They will lead the same conclusions or same equations, same numbers. So in the second version, we have the drain, and here is GM VGS. Then you have the gate. Then you have the source here, and between the source and the gate there is 1 over GM, and here is VGS. Okay, and then the gate is connected to our signal, V signal, then the ground, The drain is connected to the ground. And here is the source. The source is connected to the load, then the ground. Here is VO between the source and the ground. And here is the input. Remember, the input is between the terminals of the source. This terminal and the ground, the second terminal, including RS, of course. Okay. So let's now, make the analysis again and get EV and R input and R output. Before anything, always the current that flows into the gate is equal to 0. So this current here, I, is equal to 0. This is, essential step. Otherwise, your whole analysis will be wrong. Okay, that's why this is basically equivalent to the first one. The first one you have open circuit. Okay. Good. So AV number 1 is equal to VO over V input. So what is VO? Let's follow this current. Let's follow the flow of this current. This current, flow in that branch. Then at that point, it should divide. It should go somewhere, some part somewhere, and second, so 2 branches. So some part will go to the first branch, another part will go to the second. But remember, I is equal to 0. So this current here, let's call it IO, is completely equal to VGS GM. So IO is equal to I plus GM VGS. I is equal to 0, so it's equal to GM VGS. So VO is equal to IORL. IO is GM VGS, and here is RL. How about V input? V input is the voltage across from the gate to ground. So from that loop here, V input is equal to VGS plus VO. So it's equal to VGS plus VO, which is GM VGS RL. So EV basically equal to VO, which is GM VGS RL over VGS plus VGS GM RL. VGS will go away, so this will be RL over RL plus 1 over GM. Let's check if this is equivalent or not. Here is AV. Yeah, it's exactly the same. RL over RL plus 1 over GM. Number 2, our input. Our input is basically V input over I. I is 0. So V input over 0. So it's equal to infinity. And that's why I told you, remember all the time, if you use this version of the equivalent circuit, to mark this current as 0. Otherwise, you have, a wrong V output, our input here. So now we're going to calculate our output. Okay. Remember again, here is the equivalent circuit after, canceling V input and putting Vx and Ix as usual. Remember that the current that flows to the gate is equal to 0, which is I here. Okay. So what is Vx? From that loop here, let's call it loop 1 or whatever. So Vx plus VGS. Remember, VGS has this direction. Minus I, our signal, equal to 0. Remember, I is equal to 0, so I, our signal, is equal to 0. So Vx is equal to minus VGS. Now, what is Ix? So here is IX is going into the gate, and GM VGS is also going into the gate, so minus GM VGS equal to 0, so IX equal to GM VGS. This is plus, yeah, so this is minus. Both are going into, so both are plus. So IX is equal to minus GM VGS. So now, based on that, RO is equal to VX, which is minus VGS, and IX, which is minus GM VGS. VGS will go VGS, minus with minus, this will be 1 over GM. So let's now compare our input and our output. Our input is infinity, our output is 1 over GM. Our input is infinity, which are right, and our output is 1 over GM. So again, using either versions of the equivalent circuit, either this version or this one, both are equivalent. I'm just showing one example to make you feel comfortable in using any of them. But for some problems, using the second one makes it really easier, especially with common gate amplifiers, or when you have RS resistance between source and the ground. Okay, but especially with most transistors or most amplifiers, the differences are not that high.